Let's learn PMMC instrument together. Okay, first we practice the diagram. At least in 3 to 2 3 times we practice. First I teach you how to draw, because as I said, we're learning it together. First, what you need to do is draw North Pole, South Pole. Very layman I'm drawing, just for reference. This is North Pole, this is South Pole. This much everybody has learned. Learn it with me, Okay? North Pole, South Pole. Then draw like this. I will tell you what is the diagram and all. First, this much I've drawn. North Pole, South Pole. This is the moving coil. This is the iron core. This is the iron core. This is the moving coil. Okay. I'll erase it for now. I'll just redraw it once nicely. I'll draw. Not nicely, but north, south. This is the moving coil. This is the iron core. Sorry, ulta I said. Outside is iron core, inside is moving coil. Okay, outside is iron core, inside is moving coil. Okay. Now what we have to draw is we have to draw one pivot like this. Okay. Like this. One at the top, one at the bottom. North pole, south pole. Then what did we draw? We drew iron core inside the moving coil and a pivot like this, and it's ending with jeweled beading. Jeweled beading. Then you have something like this. This is lower control spring. This is upper control spring. To the upper control spring, a balanced weight is attached, like something like this, and this PMMC. Okay. Some point like this is there. 0, 1, 2, 3, 4. Something like this is passed. Okay. This is U-shaped permanent magnet. U-shaped permanent magnet. Lower control spring. Your current goes out. This is lower control spring. This is upper control spring. Here current goes in. Okay. This is jeweled bearing. This is pivot. This is iron core. This is moving coil. And balance with all that. This is pointer. Diagram have we learned? Is it easy, the diagram? Slowly we will learn. Once again we will draw without seeing. North pole, south pole. U-shape permanent magnet. Iron core, moving coil. Pivot. Pivot. Upper helical spring, upper control spring, lower control spring. This is the pointer. 0, 1, 2. This is uniform scale. Okay. This is north pole, south pole. Lower helical spring, jeweled bearing, pivot, upper helical spring, I in, I out, I out, iron core, moving coil. Balance it all that. Okay. That's it. Construction. Are we ready with the construction? Yes. Now working, I will show you the slides and we will slowly learn. No issues. Once again, you want to draw sure. North pole, south pole, permanent magnet. Then you have iron core. Then you have moving coil. Let's say magnetic coil. Then no, it's moving coil. Then you have the pivot, which is jeweled to the bearing. Then you have upper helical spring, I in, along with that this balanced weight is there. Pointer, which is showing to a uniformed scale. Here you have lower helical spring, which is I out. Okay, done. Major it is done. Now what least we will see. We took 5 good minutes to learn the diagram, which is very nice. Okay, so permanent magnet moving coil instrument, PMC is permanent magnet moving coil instrument. Okay, so when a current carrying conductor is placed in a magnetic field, a force acts on it. Due to this force, the coil rotates and the pointer moves over the scale. Very simple. When a current carrying conductor is placed in a magnetic field, force acts on it. When a current carrying conductor is placed in a magnetic field, force acts on it. Because of this force, the coil rotates and the pointer moves over the scale. Okay, don't worry much. This construction, let's see. A strong permanent magnet produces the magnetic field. There's two magnetic fields. Okay, first one is produced by the magnetic field, north pole, south pole. Next one, a light moving coil is placed between the poles of the magnet. We saw in the diagram. Okay, a soft iron core is placed inside the coil. Inside, but according to the diagram, it was outside. Okay, fine. Maybe diagram is only wrong. Just give me a minute. Let me cross check, because in the diagram which I have referred to is given by the teacher itself. So just let me cross check. Okay, moving coil is outside. Okay, moving coil is outside. This diagram just change everything. This becomes the moving coil. This becomes the iron core. So the coil is, okay, soft iron core is placed inside the coil. Core is placed inside the coil to make the field uniform. Why is the first one is permanent magnets are there to produce a magnetic field. Second one, a light moving coil is placed between the poles of the magnet. A soft iron core is placed inside the coil to make the field uniform. The coil is connected to a pointer. Actually, coil is not connected to the pointer directly. Right? Coil is not connected to the pointer directly. We can say that just give me a second. Coil is directly not connected, but that's what little not very right I'm feeling. The moving coil is attached to the spindle, and the spindle is also attached to the pointer. Okay, so the coil is attached to the spindle is attached to the pointer in turn. Okay, so the coil is connected to the spindle and the spindle is connected to the pointer, which moves over the scale. So the two springs, spiral springs, provide controlling torque and carries the current to the current. We can just say this in upper helical spring construction. You can just tell by your own, no issues. Eddy current damping is provided for quick working here. That you leave construction by seeing the diagram. Or whatever you feel like writing, right? Working when DC current. Remember DC, PMMC, only DC, no AC. When DC current flows through the moving coil, a magnetic field is produced. When DC current flows through the moving coil, a magnetic field is produced. The coil is already placed inside the magnetic field of the permanent magnet. First one is the permanent magnet is producing the magnetic field. One more is when current is flowing through the magnetic moving coil, again magnetic field is produced. What are the two magnetic fields? One is already, as the moving coil is placed in between the magnetic permanent magnets, magnetic field is produced. Second one is when DC current flows through the moving coil, a magnetic field is produced. Because of the interaction of the two magnetic fields, a force acts on the coil. This force rotates the coil and the pointer moves on the scale. So since the moving coil is attached to the spindle, here they have not spoken about spindle, but I will tell with respect to the spindle. Okay, since first two magnetic fields interact with each other, this is that moving coil experiences the mechanical force and starts rotating on its axis. Since the moving coil is attached to a spindle also rotates. As a result, aluminum pointer will deflect on a calibrated scale. At the same time, what happens? The spring which is there, right? Upper control spring, lower control spring. The springs are getting twisted and they produce sufficient controlling torque. So the deflection torque is there. Controlling torque is a damping torque. Is a deflection is produced by the interaction of the two magnetic fields produces a force which turns the coil. That is deflecting torque. Controlling torque is produced by the two springs. They get twisted and they produce controlling torque. Damping torque is whenever it's produced by eddy current. Eddy current is damping. the pointer stops and deflecting torque becomes equals to the controlling torque. Okay. PM works only on DC. If AC is upright, the direction of the current changes continuously, so the torque changes direction, the pointer cannot show proper reading. Okay. So torque, this is important. How will you remember? I will tell you. Remember as Bina. Bina. TD equals to Bina. Don't get confused between this torque equation in PMMC and the torque equation of the DC motor. That is totally different. It's totally different. Please don't get confused. So N is the number of turns of coil, B is the flux density, A is the effective area, I is the current to the coil. So after this, TD equals Bina, BNA is G. So TD equals GI. Why? Because BNA equals G. Okay. Here we got. So the spring provides controlling torque. Sorry. TC equals K theta. This is deflecting torque. Okay. Deflecting torque, controlling torque. Only you have to do. TD, you understood how we got TD equals Bina. So BNA equals to G. So TD equals to GI. That is done. Controlling torque. TC equals K theta. K is the spring constant. Theta is the angular deflection. So when TD equals to T, it is that time only the pointer will come to rest. TD is what? GI. This is what? K theta. Theta equals to gk by I. So theta is directly proportional to I. It's a linear relation. That's why the point is directly proportional to the current flowing through the coil. That's why it has a uniform scale. Understood? Any three advantage, disadvantage: uniform scale, low power consumption, effective eddy current damping. So you remember, first of all, it has uniform scale, and then low power consumption, and then effective eddy current damping. Disadvantage: it can be used only for DC instruments, costlier than moving iron instrument. Error may occur due to aging of spring and permanent magnets. One quick revision shall we do? Quick revision. 12:20 now, by 13:20 we should finish. Such revision. This is correct or again wrong? Coil is outside. Okay. Look at the here. Core is placed inside the coil. So coil is outside. Remember aluminum coil we used to wrap, right? Remember it like that. Okay, my time don't consider now. Okay. Something I told. This is balancing weight, aluminum pointer, deflection scale, all of that. So first construction we can explain with seeing the image itself. Working when DC current flows through the moving coil, magnetic field is produced. Okay. Next, the coil is already placed between two permanent magnets, which produces magnetic field. The interaction between the two magnetic field produces a force. This force turns the coil. As the coil turns, the spindle is attached. With the spindle is attached to the coil also rotates, which deflects the pointer in the calibrated scale. At the same time, the upper and lower control springs get twisted and they provide controlling torque. Eddy current damping is done to prevent oscillations. Correct. So to damp out oscillation, we use damping. Here we are using eddy current damping. That's it. Simple. Was it hard? No. But after whenever deflection torque is equals to controlling torque, it comes to rest. The pointer comes. That is important. And this, after the writing all this, don't forget to write the derivation. For damping torque, TD equals to Bina. BNA equals G. So TD equals GI. That much we need damping torque. Controlling torque, TC equals K theta. Then TD equals TC. So GI equals K theta. Theta equals to GI by K. As theta is exactly proportional to I, we can say that This is why the scale is uniform. That's it. Done. So thank you for watching. See you in the next one. Bye bye.